Hey everyone, and welcome to The Explainer. Today, we're going to pull back the curtain on one of the most brilliant tricks in all of computing. It's this hidden system that lets our devices do way more than they physically should be able to.
You ever just look at your phone or your computer, right? You've got like 20 apps open, 100 browser tabs, and you just kind of wonder, how is this thing not on fire right now? How can you edit a massive 4K video file when the file itself is bigger than the amount of memory your computer actually has?
Well, the answer is this absolutely clever illusion. It's a memory management technique that basically tricks your computer into believing it has way more memory than it physically does. And to get our heads around it, we don't need to dive into a bunch of code. Nope. We can start with something much simpler.
To really unlock this idea, I want you to just imagine your computer's memory as a workspace. You know, like you're studying. You've got your desk right in front of you, and over in the corner, you've got this huge bookshelf.
Okay, let's map this out. Your computer's RAM, that's your desk. It's pretty small, you can't fit a ton on it, but anything that's on the desk is right there, super fast, ready to use in an instant. Your hard disk, or your SSD, that's the giant bookshelf. It can hold a massive library of books, but, getting up, walking over, finding the book, and bringing it back, that's a much slower process. And the specific book you're reading at this exact moment, that's the data your program needs right now.
All right, you got that desk and bookshelf idea locked in your head? Good. Because now we're going to see how that simple concept gets built into the real system, humming away inside your computer. We're trading the analogy for the actual tech.
And here it is, the star of the show, virtual memory. This is the official name for the technique that lets the operating system use that slow bookshelf, the hard disk, as if it were just an extension of your fast desk, the RAM. What this does is give every single program the illusion that it has this enormous private workspace all to itself.
Now, to keep all this organized, the system is smart. It doesn't move data around one word at a time. It moves everything in fixed-size chunks. In the program's imaginary world, these chunks are called pages, and the physical slots in the actual RAM where those pages can land, those are called frames. Just think of them as standardized boxes and perfectly sized shelves. A page is a box, a frame is a shelf, and they're all the same size, so everything just fits perfectly.
So who's the librarian in all of this? Who manages this whole system? Well, the hero of the story is a special piece of hardware called the Memory Management Unit, or MMU for short. And its job is to be an incredibly fast translator. When your program says, hey, I need the data at my imaginary address, number 500, the MMU's job is to instantly figure out, okay, where is that actually located in the real physical RAM?
But what happens if the book your program needs isn't on the desk? What if it's still way over on the bookshelf? That event has a special name. It's called a page fault. Now, this isn't an error, not like a crash. It's more like a signal. The MMU basically throws its hands up and yells for help. It tells the main operating system, hey, I can't find this page here on the desk. You need to go fetch it from the slow hard disk and put it in RAM for me.
And this brings the whole flow together perfectly. Check it out. First, your app asks for some data at a virtual address. The MMU looks up that virtual page in its special map, which is called a page table. Now, if the page is already in RAM, bam, that's a hit. It's super fast, you get your data instantly. But if it's not there, that's a miss. A page fault happens. The operating system has to jump in, go find the page on the hard disk, and swap it into an open spot in RAM. It might even have to kick another, older page out of RAM to make room. So you can see how this whole system feels almost like magic, right? But this magic definitely comes at a price. Using that hard disk is fundamentally, unavoidably, slower than using RAM, and that difference creates some really important trade-offs we have to talk about.
I mean, the advantages are just world-changing. We can run enormous programs, things that are way bigger than our physical RAM. We can multitask like crazy because the OS only needs to keep the active parts of each program on the desk at any one time. And this one is huge. It provides memory protection. Every program lives in its own little virtual bubble, so a bug in one app can't reach over and mess with the memory of another one. This is literally the bedrock of modern, stable operating systems.
But here's the catch. Here's the big but. Every single time a page fault happens, the system has to make that slow trip to the bookshelf. And going to the disk isn't just a little bit slower. We're talking thousands, sometimes millions of times slower than just grabbing something from RAM. A few of those trips are totally fine, but what happens when there are too many?
Well, that leads to this disastrous condition called thrashing.
This is what happens when your system has so little free RAM that it's just constantly, and I mean constantly, swapping pages back and forth from the disk. It's like trying to work at a desk the size of a postcard. You'd have to swap books from the shelf for every single sentence you read. You'd spend all your time just moving books around and no time actually doing any work.
And this chart just shows how devastating thrashing really is. Your computer's CPU is pegged at 100%, the little hard drive light is blinking like crazy, but your computer is doing almost nothing useful. It's spending 95% of its energy just shuffling data back and forth. Your whole machine grinds to a halt, not because the processor is slow, but because it's literally starving for data it can't get fast enough. Okay, so after all that technical detail, let's zoom all the way out. Why is this so important? Why does this matter to you?
Because this isn't just some dusty computer science theory. This beautiful, complicated dance between your hardware and your software is happening billions of times a second, right now, on the very device you are using to watch me. It is the silent, invisible engine that makes your entire digital life possible.
And when I say it's everywhere, I mean it's everywhere. The Windows PC on your desk, the MacBook at the cafe, the giant Linux servers that power the entire internet. It's the core system for your Android phone, for your iPhone. From the biggest supercomputers on Earth down to the phone in your pocket, every single modern device depends on this idea to even function.
So here's the big takeaway. Virtual memory was a genius hack. It completely shattered the physical limits of hardware and made the complex, multitasking world we live in today possible. It solved a fundamental problem of its time. And that just leaves us with a really fascinating question. What are the fundamental limits we're hitting today, and what's the next brilliant illusion that's going to be invented to solve them?